maybe from time to time, I just look if anybody wants to say something. Okay. Okay. Good. Yes. Then I just start. Yeah, I will talk about thick accretion disk models around black holes. And let me first thank my collaborators, whose names you see here. So Audrey Trova, Shokufe Paraji, Christian Pfeiffer, Sebastian Bahamonde, Emanuel Schlake, and Jan Hackstein. And yes, let's jump right into the topic. We lost already so much time. So as you all know, so I'm basically interested in the strong gravity regime, and this means, of course, basically that I'm interested in compact objects who strongly curve the space-time. And then if we have material around these compact objects, and they are collected in an accretion disk, then this material can probe really deeply into the strong gravity regime and give us some information on what is going on close to, say, black holes. And black holes are particularly interesting because they are, in a certain way, pretty simple objects. So you probably all know the no-hair theorem, so which states basically that if you have an isolated black hole, then you have only to care about 3 parameters, and this is the mass of the black hole, its angular momentum, and its charge. In general, electric and magnetic charge, but magnetic monopole charge is, of course, highly speculative. And then, in addition to that, if you look to astrophysics, then usually you even neglect this charge parameter here. And the reason for this is rather straightforward, because the gravitational force is much smaller than the electromagnetic force. We will have, if we have some charged charged black hole, we will have some selective accretion of oppositely charged particles from the environment. And this then will cause that the net electric charge will very quickly decrease to very tiny values. So if you look at this charge parameter, capital Q, that you find, for example, the Kerr-Newman metric, then this will be very, very small, below 10 to minus 18. And even if you do not have any environment where you have these oppositely charged particles available, even then you will have some pair production. And this will also already lead to a rather small parameter of the electric charge, Q, which should be then lower 10 to minus 5. This was already estimated in the 70s. And just to remind you, so this capital Q here is in geometrized units, and it is related to the SI units by this conversion factor here. Okay, so what exactly is now accretion? So we are thinking of a central black hole. Then we have some matter around this compact object, around this black hole. And for example, this is a very common model for active galactic nuclei. So for the supermassive black holes that we have in the center of our galaxies. And then this material that is orbiting this black hole will be gradually absorbed by the central black hole. And this will then cause very prominently observable effects. For example, we will have X-ray emissions, we will have jets, that is what is indicated here. And also this is, of course, the reason that we can observe these shadows. And the idea is that due to this, we might get some information of the strong gravity regime. Okay, so after this short introduction into accretion, I want to talk about in more detail about a specific accretion disk model, the so-called polished donut model, and I will give you some mostly basic ideas here. And then I want to discuss this model in 2 different ways. First, I want to explore alternative gravity theories and their impact on this accretion disk model, this polished donut model. On the one hand, I will discuss a specific theory, the so-called Born-Infeld teleparallel theory, and then I will talk about a parameterized framework that catches many theories. And then the second point that I want to address is the impact of the electromagnetic environment on the accretion disk model. So first, I want to discuss about charge disk, and then there are two different approaches to construct these, and I will go a little bit into both before I summarize. So by the way, you can please, if you want to ask questions, somehow try to catch my attention, and I'm happy to answer questions at any time during the talk. Okay, so let's start with this accretion disk model. And as I didn't know what is exactly your background, I started really basic. So if you think this is too basic for us, I don't need this information. I'm happy to jump over some parts here. So what is the general idea? So we have, let's assume that we have some particle that is moving on some stable circular orbit around some black hole, or actually also around some star or something. Then we will have some relation between the radius and the angular momentum. And if we want to get this particle into the black hole, we somehow need to decrease the radius. And due to this relation here, you can only do that if you somehow lose the angular momentum of the particle. So if you somehow manage that, to lose this angular momentum, then the particle will go inwards, and this in turn means that the velocity of this particle will increase, and it would follow this Keplerian profile here that I wrote down here. Oh, this 2 should be here. This should be a square here. And so to make this accretion happen, to make this particle here fall into the black hole, you somehow need to transport the angular momentum outwards to transport the mass inwards. This is the very basic idea of accretion. And now we don't have single particles, of course, we have some disks that are going around the black hole. And if we then look at this slightly more complicated setup, then we will have some inner ring, A here. This will move faster than the outer one. This means there will be some friction between the two rings, which I labeled here A and B. So the friction will slow down A and speed up B. And by this, heat will be generated, the angular momentum will be transported, and A will then finally move inwards and B move outwards. Of course, if you have an additional ring, then this process continues throughout the disk. Okay, so now there are several, so there are several accretion disk models around who basically differ in the assumptions how this angular momentum should be transported. So first thing to notice is that for this angular momentum transport piece to be efficient enough to explain the accretion rates that we see in the sky, it is not possible to do that just via molecular friction. This is many, many orders of magnitude too small. And this means to make this momentum transport happen on the scales that we need, you have to invoke some turbulence model. Usually this is the so-called magnetorotational instability. But okay, I will not go into this. And then you have some basic disk models based on that. And probably the best known and very basic model is the Shakura and Sonyaev thin disks. This was developed, I think, in the 70s. And what they do is that they assume an effective viscosity. This is also called the alpha prescription. Also, these disks are sometimes called alpha disks. And you see here right a diagram that I took from the review of Abramovich and Fragile, this living review. And you see here in this diagram the optical depth over the accretion rate, and also you see here the height over the radius. And then you see here the Shukura-Tsonyaev disks, so they are thin. The radius is large compared to the height. And then you see also some other models here. The slim disk developed from that with some other assumptions. And then you also have some which have like comparable height and radius. And then there is another model which is usually called a thick disk or a polished donut model. And you see them up here. So the height is high compared to the radius. And in these disks are constructed by assuming that or by neglecting the viscosity. Okay, what does it mean in more detail? So if we look at these thick, so geometrically thick, there are also optically thick disks around, but I'm talking about geometrically thick disks. The idea is to have a fluid that is in hydrostatic equilibrium close to your black hole. So we expect that close to the black hole, the disk should be thick. There's some argument to that. And so we also assume that we have a high accretion rate at or above the Eddington limit. So the Eddington limit, if you don't know that, this is derived from setting equal the gravitational inward force and the radiation pressure pointing outwards. And it is assumed that it has a very low viscosity and that it can describe the region close to the black hole. And of course, to build such an analytical model of accretion, you have to make some assumptions, symmetry assumptions mostly. So you assume that this whole setup is stationary and it is axially symmetric, and also that you have some reflection symmetry to the equatorial plane, although there have already been generalizations who do not assume that. So stationarity and axial symmetry is the most important ingredient. Then you assume that your matter is described by a perfect fluid and that you have some equation of state. Usually you use a polytropic equation, but this is also not in all models done like this, but in the classical one. And then you assume that your fluid moves purely circular. This sounds very strange, because this means that you actually have no accretion in this model. So the accretion in this model, if you look at this picture here, you see that you have here some cusp at the inner part of the disk. And it is assumed that here you have an overflow over the disk where you will then develop some streams onto the black holes. But these streams itself are not part of this analytical model. And last but not least, you usually assume that you have a test fluid. So it means that the fluid that you're considering here does not influence the space-time. So it's much less heavy than the central black hole. Okay, so what are the basic relations of this model? First, the most important ingredient is energy conservation or energy momentum conservation, given by this equation here. Then you assume that you have a perfect fluid, and then from energy conservation perfect fluid, you can derive the Euler equation, relativistic Euler equation, which I wrote down here. So P is the pressure, epsilon is the energy density, H is just the projection. And then you put in your assumptions of the model. So you have circular motion, which means that your forward velocity has only a t and a phi component. Then you introduce the specific angular momentum, like this here, and your angular velocity, just d phi by dt. And then you use your normalization of a time-like flow to find the acceleration that is acting. And then you can find this expression here. So it's basically given by ut and your two parameters here, the angular momentum and the angular velocity. And once you have this from your circular motion, you insert it back into the Euler equation and derive the equation that governs your model. And it's just like this in the classical approach. So the point that you then need to make is to look if you can integrate that, and to ensure the integrability, you have to you can derive the von Zeipel condition if you have a barotropic fluid. So if you have some functional relation between energy and pressure, and then you can show. I didn't put the reference, but this was also developed in the 70s, and you can also find it, for example, in Miesner, So, and Wheeler, that the surfaces of constant pressure and constant energy density coincide if and only if the surfaces of constant L and omega coincide. This is a very nice result in Newtonian physics. This boils down to that you have cylinders where all of these things are constant. So then usually what is done, or it's classically done, is that you consider the L equal to constant case, because this is like most easy choice that you can do. The omega equal to constant, so angular velocity constant case, does not work in the sense that you cannot find bound structures, bound accretion disks. Yes, so you take these assumptions, you define an effective potential, which is basically just the integration of the left-hand side, and then you can find these closed surfaces for negative W. And if you look at the picture here, this is a very old calculation. You see here the equipotential surfaces, which coincide with the equipressure surfaces and equi-energy density surfaces. And you see that you can basically choose any of these lines here as the outer boundary of your accretion disk, and then just one. And yes, L is here between the ISGO value and the marginally bound value, and there is one particular equipotential surface which has this self-crossing that you see here, and this is the cusp that I mentioned earlier. So for this particular disk, it is assumed that the mass can flow over this point here like a Rochlov overflow and stream onto the central black hole. Then there are some rather interesting specific points in this model, and this is that you have the center of this disk, which is the SIG disk, which would be approximately here in this picture, and the cusp, they are marked by the extrema of your potential, and on these points here, you actually have geodesic motion. So this is very nice. It means that with looking at your geodesics, you can already get some idea of where your accretion disk might be. And then you can construct your disk, and you will find that usually the center is at the marginally stable orbit, or the ISGO. This is the same thing. So the point, the closest point to the black hole where you can just have a stable circular orbit. And this cusp here, the self-crossing, this happens approximately at the radius of the marginally bound orbit. So this is the bound orbit, unstable bound orbit, or circular orbit, where if you perturb it a little bit, it can just reach infinity. So for a Schwarzschild spacetime, the marginally stable orbit is as 6m, and the marginally bound orbit is at 4m. Okay, so this is the basic idea how to construct these polished donut models. And now, building on that, I want to discuss some modifications of that. So let's first go into some alternative gravity theories. So the main question that we ask ourselves is, can we find some notable or maybe even non-perturbative effects on these SIG accretion disk models close to our black holes? And then basically you always have like two ways to do that. First, you could go and study a specific theory, case by case. And we explored one possibility recently, the Born-Infeld teleparallel series, basically f of t theory. And then the other idea is to follow in spirit the PPN approach, so that you have that you introduce some parameters, free parameters into your metric that you then constrain from observations, and then you just translate this to the parameters of the respective theory that you are interested in. Okay, so let's first talk about this Born-Infeld gravity. This is a specific choice of f of t gravity, where t is the torsion. And the nice thing about this specific theory is that there was recently discovered that you can formulate an analytical solution of the field equation, and if you assume spherical symmetry. And the solution can be written like this here. So you have two free functions here, which only depend on the radius, capital A and capital B. And they are given explicitly. You see here the first part is the usual Schwarzschild part. And then you have a correction, which goes with a free parameter lambda. And if lambda goes to infinity, then this part here will go away, and you will recover the usual Schwarzschild solution in GR. The same holds for this function b here, which is in Schwarzschild just 1. And then again, if you study here the limit for lambda to infinity, you find that this goes to 1. And then we started to analyze this metric with a goal to derive some thick accretion disk. But what we first noticed, and which was somewhat surprising, was that if you study the ADM mass of this metric here, which you can calculate like this here, and then you do a weak field expansion of this, then you can, so post-Newtonian expansion, then you can compare this to this parametrized post-Newtonian framework that I mentioned before. And if you're a little bit familiar with that, you probably know that there are two free parameters here, beta and gamma, and both should be 1 in general relativity. And if you do this for this particular theory here, then you will find as well that gamma is equal to 1, but beta is not. And this was surprising because there is some theorem around that these teleparallel theories should coincide in their PPN limit with GR. But it turned out that upon closer inspection, actually this theorem does not apply to this particular f of t theory here. So as we thought initially. So it turned out that you can derive a bound on this lambda just from the beta parameter, which is heavily constrained by solar system observations. And then this implies a bound on lambda should be larger than approximately 140. This was, well, in a way, of course, very nice because we found a constraint on this parameter. But on the other hand, it was a little bit disappointing because it basically meant that we will not find any notable influence on the thick accretion disk. So we first studied like the important radii that I mentioned before, the marginally stable orbit or ISGO, and the marginally bound orbit. And this was here the first order correction to that, to these respective radii. And you already see if lambda is large here, of course, it will very fastly decrease and almost match the Schwarzschild values. And then if you construct the thick disk, here on the left-hand side, you see the Schwarzschild result. On the right-hand side here, you see the smallest lambda that you are allowed to take. And you immediately see there's almost no difference in the equipotential surfaces. And we also quantified this a little bit more by calculating the maximal potential difference that you can get here, and compared it to the Schwarzschild value and plotted it over lambda. And you see that for lambda larger than, say, 140, somewhere here, the correction is very small. In particular, if you compare that to the correction that you will get from a rotation to this value, which is about 0.5. So this is many orders of magnitude larger. So any correction due to this lambda will completely be masked by any very, very slight rotation that you introduce into this system. Okay, so this was a bit disappointing, but then we went on to study this parametrized space-time, and I will say a little more to the reason in a second. So first, to introduce a little bit to that, it is a theory. This is a theory-independent model of just some space-time. So this metric that you see here is not supposed to be the solution to a specific field equation or something. It's just some model that you write down to work with. And this particular form here was first developed by Retzoller and Sidenko in 2014. And they wrote this here, and they expanded these three functions here, capital N and capital B, in a partial fraction decomposition. Yes, but then some years later, Knopia and again Sidenko studied this with more detail, and they found that actually it is mostly sufficient to just work with three parameters here in this metric, and then you get a form for these metric functions N and B that I wrote down here. And here this R0 is one of the horizons of this space-time. And actually, when this was constructed, it was supposed to be the outer horizon, but this is actually not quite true. I will comment in a second. But before, let me point out that in this expansion in 1 over r that you see here, notably the 1 over r squared term is missing. And the reason for that, and also here the linear term 1 over r is missing. And the reason for that is that these two terms are exactly very much constrained by these parameters beta and gamma from the parametrized post-Newtonian formalism from the weak field observations. On the other hand, the parameters that remain here, these epsilon A1 and B1, they control what is happening in the strong field regime close to the black hole. And these are not really constrained by weak field observations. So with this, you can really play around better, so to say, without running into these problems that that you have these heavy constraints on the space-time. And by the way, when you calculate the epsilon A1 and B1, you cannot do that for what we discussed before, but because this Born-Infeld expression here, this will go with the 1 over r squared, exactly, and the 1 over r here. Excuse me. Okay, as I said, this R0 is supposed to be a horizon of the space-time, and we analyzed this in some more detail, and we found that actually it's not the outer horizon, so the event horizon, in all the parameter range. So here you see on the x-axis the parameter epsilon, on the y-axis you see A1, B1 is not important for the horizons. So only in this shaded region here, you will have that this is the outer horizon. If you go outside of this region, you have to be careful what you're doing. So, and in addition, when you analyze this, this metric, you find some peculiar features, say. In particular, you can find that the GTT component, so this n squared here, this can have extrema outside of the event horizon. And this has the consequence that you can have in this shaded region here, for these parameter values, you can have static orbits that are just sitting there around the black hole, right? They are like, this means that you have something like a negative gravity effect or something like this, yeah? So they are just sitting, you can construct geodesics, which are static, so they're just sitting there without moving close to the black hole. So this is somewhat peculiar, of course, and maybe not very physical. Okay, so we also studied the important radii here. I only give you the marginally stable. The marginally bound behaves very much the same. So you can derive the first order corrections to that. And now here you see a plot how this marginally stable orbit evolves as a function of this parameter epsilon. Oh, I didn't say it. So this epsilon basically controls the position of the horizon in your spacetime. And here you see this parameter A1. This is higher order corrections. And then you can see, okay, there are regions which are very, say, sensitive to changes in the parameters, and regions, for example, here, where you barely notice an influence on these radii when you slightly vary the parameters. So this is like for epsilon between, well, up to 1 on both sides. If you zoom out, you find this here, and you notice here this strange numerical artifacts that you see here. And this comes because these are the regions where you have these extrema here, or approaching this region where you have these extrema here. And there you run into problems because it might happen that you don't have any marginally stable orbits at all. So it could be that you have just stable circular orbits, then you have a region where you have no circular orbits at all, and then again some unstable region of orbits. So these behave quite differently from Schwarzschild in these extreme parameter ranges. Okay, so what is then the impact on these polished donuts, accretion disks? So we compared the disks in different spacetimes, so meaning for different combination of parameters. And this is, of course, always a little bit difficult to compare results in different spacetimes because you have the ambiguity with the coordinates and so on. Also, for the construction of this thick disk, you have to choose some angular momentum, some constant angular momentum, and it is not clear how to fix this a priori, so to say. So what we did here is that we always chose in all these different spacetimes the marginally bound torus. So if you look at this sketch here on the right, just as a reminder, what we call the marginally bound torus is the one which has this cusp here. So the one where you can actually have accretion over this crossing here that flows onto the black hole. So we decided to always in all spacetimes look at this particular unique equipotential surface. And then to compare the results in the different spacetimes, we calculated the distance from the cusp here to the center of the disk. And this is what you see here in this color plot. Here you have again the epsilon and the A1. Here again you see problems because here you don't have really, these do not exist, these radii, so you have problems to calculate that here. Then probably I would not trust here this result in this region here. But what you see is that this basically follows closely what we already saw for the marginally stable orbits. And again, you have these parameter regions here where you are very sensitive to changes in the position of the horizon, so in changes in epsilon, not so sensitive in changes of A1. And then you have farther out, you have regions where we can vary the parameters in a neighborhood without having much impact on the shape of, or on the radial extent of your disk. You see here the code is between 1 and 10, what we plotted here. Okay, so a question that we also ask us is, are there maybe some like distinctive features that you can find here? And of course, a candidate for this is this region where you have strange behavior of the GTT. And if you do that, you can indeed find something like this. You can, in these spacetimes, for specific choices of your parameters, and here I gave you one example of that, where you can have multiple tori in the equatorial plane, or where you can have rigidly rotating tori. This is not possible in GR, right? In Schwarzschild or Kerr spacetime at least. So this is also a quite distinctive feature. But as I said, this happens mostly in, or at least towards, the regions where this GTT has some extrema. So where the spacetime itself is somehow strange. But if you do that, then you can have different combination of these cusps. They can connect the two. If you can have two tori, and then they can be connected by a cusp. It means that you can have mass movement between the two tori, or you can have also that that one of the tori is just self-contained, and the other one has accretion onto the black hole, and so on. You see this on the left here. You see some effective potential, and then the idea is you can fill this up like with a fluid, right? And then we plotted here two different cases and the corresponding shapes of the disk you see here on the right, and the different colors matching these effective potentials here on the left. And here you see this inset here where we plotted the smaller inner torus, and which you can then see here. And if you vary this angular momentum here, then you can also have them merge or disappear or whatever. And for the rigid rotation case, you can, for example, find something like this here. So you can find an effective potential which is given like this here. So usually the problem is in Schwarzschild you will not have this maximum here. So you cannot just fill some bound structure. But for this more peculiar spacetimes here, this is possible, for example, for this combination of parameters. Before I close this, I just want to give you some note of care here. So we also studied if you can, like, from a given structure of a disk or from given radii of the significant radii, if you can construct the parameters of this spacetime. And this is not uniquely possible. So from these observations, usually you have two solutions, maybe sometimes more solutions of parameters that gives you the same disks. So this is somehow a problem if you want to reconstruct from observations these parameters or constrain these parameters from the observations. So this is not a very nice feature, and one has to think more closely if one wants to use this parametrized spacetimes, how to somehow get rid of this, or if there is some like combination of observations which can resolve this ambiguity that you have. And then the second note that I want to make is that although these multi-tori and rigid rotations are nice features that you might have from some alternative theory, you can also generate something like this in GR if you consider additional effects, as we will actually see in the next minutes. Okay, so this is what I wanted to say about alternative gravity theories in thick disks. And now I want to come to the electromagnetic environment. I still have like 15 minutes. Is this correct? Somebody say something. Yeah, okay, thank you very much. Okay, so first point that I want to make is why we want to consider charge in this setup. So I argued in the beginning of the talk that astrophysically, you can actually neglect the charge of the black hole. But this is not the complete story, actually, because the Noether theorem or conjecture only applies if the black hole is isolated, right? So, but if you have some electromagnetic fields in the environment and the black hole is rotating, then the rotation will interact with these fields, and then you can have actually an upcharging of this. So if you have some magnetic field, say, created by your accretion disk, or even from the galactic field, or say from some magnetar, which is in your vicinity, and then you have some interaction of the rotation with this, then you can actually create a selective accretion of charged particles. This was, for example, demonstrated in a very nice paper by Walt in 1974. He showed that if you have an asymptotically uniform magnetic field, then you will have some resulting charge of the black hole that is proportional to the magnetic field strength in this way here. So Q is given by 2 times the rotation parameter times the magnetic field parameter. So this actually means that it's not quite true that astrophysical black holes will have a vanishing charge. Due to this interaction of the rotation with the fields in the environment, you can actually acquire a tiny but non-vanishing charge to mass ratio, which should, however, be many orders of magnitude below unity. So if you want to, and just to give you some idea of this, so there was some estimate for the charge of Sagittarius A star, the supermassive black hole in the Milky Way, in 2018, which was based on the observation of Bremsstrahlung. And the result was that in SI units, the charge of this supermassive black hole is below, say, 10 to 8 Coulomb. Or if you express this in geometrized units, then this means that this is below 4 times 10 to minus 19. So this is very small. Okay. So what does it mean? It means that actually the influence on the space-time geometry should be very small. However, as we already argued before, the electromagnetic interaction is much stronger than the gravitational one. So the question remains, is there maybe some impact of this very tiny charge parameter on charged particles that are in the vicinity of the black hole? And we can do some very rough order of magnitude estimate here. So let's assume that we have a Kerr-Newman black hole with, say, a charge of 10 to minus 19. Then you look at the equations of motion for charged particles. They contain some product, small q times capital Q, where small q is a specific charge to mass ratio of the particle that you're looking at. And then you can estimate what does it mean, what is this small q if you have some electrons, say. And because of this conversion between the SI units and the geometrized units, you find that this is actually very, very huge. So this is about 10 to 21 for the electron and 10 to 18 for the proton. So this means if you build this product here, this is actually not really negligible. This is of order unity, say, roughly. So it should be taken into account. And then we also studied this some time ago, 5-6 years ago, with a bachelor student of mine. He calculated the impact of the electromagnetic fields on the ISGO of a charged particle. And here you see a result of this. So here you have some fixed ratio between for this combination of charges, specific charges, or in geometrized units again. And here you see how the marginally stable orbit, or the ISGO, evolves with the field strength, with the magnetic field strength. And you see that the impact can actually be rather strong. So the follow-up question that one can ask here, so is there then also some strong influence on the SEC disk as well? Okay, so let's go back a step and look again at the construction of these polished donuts models, but now assuming that we have some electromagnetic field in the environment. So we have some vector potential here. We assume that this field should respect our symmetries. So it should still also be axially symmetric and stationary, meaning that we have this particular form of the potential. So then we assume that our matter is a charged perfect fluid, but because our fluid is also test fluid and we don't want to consider the self-electromagnetic interactions here, we assume that the field that is produced by the charge within the disk is actually negligible as compared to the field external to the disk. So either the electric charge of the black hole or some external magnetic field that is around, for example, the uniform field that Walt discussed, or some dipole field that is attached to the central object. And then you take, again, energy momentum conservation, and you take Maxwell's equations, and then you combine them in very much the same way that you did before. And what will come out is this equation here. You might maybe recognize this first part here. This is here for the usual non-charged disk. And then you get these two additional terms here from your electromagnetic fields. Okay, and now what usually people do when you look at numerical simulations of accretion disk is that they assume some ideal MHD, so magnetohydrodynamic, which means that you assume an infinite conductivity. So this parameter sigma here is assumed to be infinitely large, which in turn means that you need to have this condition here fulfilled to have a finite expression in Maxwell's equation, or Ohm's law, actually. And then if you calculate this was done by Bonazzola in 93, you get some implication of that. And the implication is that either you need to have that your A phi component of the electromagnetic potential is a function of the angular velocity of your fluid, or that you should have a constant angular velocity, and AT and A phi are related like this. And this is both a little bit not what we want, right? I mean, this A phi is supposed to be something which is external to the disk. So it's rather strange that this should be given by the angular velocity of the disk. So this should actually not be related in the physical situation that we have in mind. And the same also, of course, holds here, that we do not want that we have this relation that is again given by the angular velocity of the disk. So this will in generally not be satisfied by the models that we're looking at, which means that we necessarily have to assume a finite conductivity in our model. Okay, so this is somewhat, not so very nice, but let's see. Okay, so we also require that we have stationarity and axial symmetry, which means that for mu equal to t or phi, this has to vanish here, right? And this again gives you a problem. It will be automatically satisfied for the classical part. It will also be automatically satisfied for this part here. But this last term here, this gives you a problem. This will in general not vanish for what we have in mind. So the solution that we came, or actually not we, but other people or before us came up with, is that we can set this conductivity to 0. So this means that we are considering the opposite limit to the ideal MHD. A different possibility is actually to assume that sigma is direction dependent. This you can also do, but the equations will in the end be the same. So for this talk, it's most easy to just assume that sigma is equal to 0. So this part of the equation goes away. So this is then self-consistent with our assumptions. And then we can follow two approaches to construct our disk. I will now first just talk about the first approach, the second one will come later. So the first idea is that we have to assume some barotropic equation of state, and then we explore our integrability condition, so the von Zeipel theorem. And this will then boil down in the end to set either L equal to constant, so the angular momentum, or omega, the angular velocity, should be constant. And if we do that, this is also what is done classically, right, in the usual models. And then in addition to that, to satisfy the integrability, we also need to take care of this term here, which comes from the electromagnetic fields. So we have to reformulate this such that we find some scalar function such that we can rewrite this term like this here. If we can do that, then we can satisfy integrability. So, and we succeeded to do that in a number of cases. So I will just symbolically put here this functional dependence. And then for the particular, then you have to actually calculate it for the particular setup that you have in mind. And then you can find some accretion gist, so some bound structure if your pressure can have a local maximum. Okay, and then we did this for a number of cases. I will not go too much into the details here because I want to mostly talk about the second approach. And this was developed in a series of papers since like 10 years or so. And the main findings have been that charged black holes and charged disks, of course, enable rigidly rotating tori, which is not possible in the neutral case. Also, if you add charge or a magnetic field, external magnetic field, then you can support something which we call polar cloud. And you see the equipotential surfaces that belong to this here in the middle. So what you see here is you have to rotate this, of course, to get the full picture. So this is kind of a cap or something that you have at the North Pole and at the South Pole of your rotating black hole. And this is rigidly rotating around this axis here. And this is rather strange because this means that you can have some equilibrium configuration at this point very off from the equatorial plane. And they're rigidly rotating, as I already said. And then if you look at the constant angular momentum cases, then it was found that that you can have double tori with this. You see this here in the left picture here. So yeah, this is also what we saw before for the parametrized spacetime, that you can have a torus here, and then you can have a cusp between them where matter can flow, and then you have an inner torus where that comes very, very close to the black hole. And then already in 2016, it was found that these charged static black holes also support off-equatorial tori. So you can have structures that hover above or below the equatorial plane, as you see here. So for example, in this case, this structure here would be some torus above, and here, because of symmetry, also below the same structure. Okay, so you can have very interesting configurations coming up when you introduce these external fields. Okay, but the main point that I wanted to talk about is nearshore approach, say. So one can also construct these disks, these charged disks, if you give or say guess angular momentum distribution. This was first done by Jarodzinski in the 1918s. This is a very nice paper. He did it only in the appendix. And then more recently, Kian and co-workers revived this method in 2009. And the idea is that you rewrite your basic equation here, classically only, of course, up to without this last term. And then you can rewrite this just in terms of your specific angular momentum here. Also the omega, there's a relation between omega and L, so this is also given in terms of the angular momentum. And then the idea behind this is that actually this angular momentum distribution, this is, to determine this is rather complicated, if not impossible, because this is given by dissipative processes, for example, by the viscosity or by radiative transfer. And still, we do not really know what is going on in these accretion disks. So important aspects here are still unknown. So it's not possible to calculate this from this angular momentum distribution from first principles. You have to introduce some ad hoc assumptions, or you have to neglect some processes, for example, the radiative transfer or whatever. So it was actually this team in Warsaw that came up with the idea that actually it's just as feasible, instead of like trying to calculate this with under some ad hoc assumptions, it's just as feasible to just make a motivated guess of how this will finally look like. And this is the idea that is behind this construction here. And then one can think about, okay, how should maybe this angular momentum distribution look like? Okay, sorry, before I say this, and one more word about how to construct this. So the idea is now you have this equation, and then you want to calculate these equipressure surfaces. And then you can assume that these surfaces are implicitly described by some function theta of r. And then you can make a derivative of that. You can rewrite this as a pressure as the derivatives of the pressures, and this derivative, this ratio of the derivatives, can actually be derived from this equation up here by just writing it twice, once for r and once for theta, and just dividing the two equations. And then the denominators here will cancel out; they are conveniently the same. And then you explicitly know this function that is called here capital F, if you know this angular momentum distribution here, L, as a function of r and theta. And when you know this, then you can solve this equation here for theta of r and determine your equipressure surfaces. So this is the idea. So you need to somehow assume this L, and how to do that reasonably. So from observations, we know that what is going on in the outer regions of accretion disk, and we know that the angular momentum is more or less Keplerian in this case, slightly sub-Keplerian. So Keplerian means actually the angular momentum of geodesics, right? Circular geodesics here. And then what we know, or what is suggested from numerical simulations, is that in the central or inner regions, this should be more or less constant, or only very slightly. And then, so this is for the radial profile in the equatorial plane. And then you need to also talk about the theta dependence of your distribution. And then again, you can look for guidance to the numerical simulations, and they suggest that you have a strong fall off towards the polar axis. And this you see also here in these two pictures that I took from this paper of Kerr from 2009, where they compare their angular momentum distribution with some numerical simulations. And you see here in the distribution in the equatorial plane, so the radial distribution, and the lines are the thick line, solid line here is their distribution. The points are from numerical simulations, and the dashed line here is the Keplerian profile. And then here below you see the distribution towards the polar axis. And here again, the cross and the dots are from different numerical simulations, and the lines are from the distribution for different choices of the parameters in this distribution. And we basically followed here this paper of Kerr So we copied their angular distribution, which is given by a trigonometric function. And then below the marginally stable orbit, we take a constant in the radial direction, a constant, and outside of the marginally stable orbit, so the ISGO, we take some distribution, which we then adjusted to charged particles here. So Kerr took the geodesic orbits for neutral particles. Here we took them for charged particles to match our assumptions. Okay, and this is then the results. Oh, I have to hurry up a bit, I think. So we discussed the charged accretion disk with the magnetic dipole field in a Kerr spacetime. So you see the sketch of the setup here. And we looked at solutions that have a center and a cusp in the equatorial plane. And the charge goes with a parameter which we call mu. This is a product of the charge of the disk with the dipole moment of the magnetic field. So if it is positive, it means that you have a positive charge and a aligned magnetic field. Or if it is negative, it has a negative charge and an aligned magnetic field, or the vice versa combinations, of course. And then we calculated the evolution of the ISGO. You see it here. What is here interesting is that this is a function. On the x-axis, you have here the charge parameter, mu, which links disk and magnetic field. And here's the radius. And you see slightly here that this actually can have a minimum here over the distribution of mu. And this you can also see a little bit better here. This is a contour plot where you have the marginally stable orbit, and you see it nicely here. So if you vary mu, here you vary beta, which is controls the radial distribution of angular momentum. And then you can see that you can have here some minimum appearing. This is rather interesting, very close also to the black hole, actually. So this is at 2. Okay, and then we discussed the height and the extent of the disks, and we found that the radial angular momentum parameter, which is called beta, controls the radial extent of the disk. This is also very reasonable, of course. So also the other parameters have also an influence, but the influence of beta is much stronger. And the height of the disk, as compared to the radius, to its extent, is mostly controlled by the charge, actually. And this you see here on the right-hand side. So in particular, if you have highly negative values of your charge parameters, then the height will increase a lot, actually. Okay, and to just give you an impression, we also calculated the shapes. Here you see when you vary beta, the disk very much extends. And if you go to very negative mu, then your disk, the torus, puffs up, so to say. Okay, good. And then we studied further the density within the disk. And we saw that the rotation almost just shifts the complete disk around, but does not much on the distribution of density within the disk. The same goes for mu. It has a little bit shifts the density, but not much. I didn't include the picture here. And then we didn't discuss anything so far about delta, which controls the angular distribution of the angular momentum. And this basically only affects the outer part of the disk, and in the inner part, it does nothing. And I also brought you here 2 examples of what we calculated for these disks. Here you see a very puffy disk where the center density maximum is very close, actually, to the black hole. And here you see a more extended disk where the density is more concentrated towards the outer parts of the disk. And if you're interested to see more of these nice pictures, you're welcome to look at our recent paper. Okay, this brings me to the end. I hope I could convince you that this thick accretion disk model is actually very nice, so very simple. They still capture the main aspects of accretion disk. In particular, if you appropriately prescribe these angular momentum distributions, you can show, this was done by Kian already in this 2009 paper, that you can really nicely reproduce time and angle average numerical simulations. Then we discussed alternative gravity theories. Unfortunately, for the Born-Infeld, there's not much influence due to this constraint from the weak field. And for the parametrized spacetime, this is more interesting. There is still room, I think, for more work to explore this parameter region. Also, you can add rotation. We already did a little bit on that, but results still pending. And then for the charge disk, yes, there we have this opposite to MHD approximations that I would really like to get rid of. And then, yes, we discussed all these nice features of equatorial tori, double tori, polar clouds, rigid rotation, and so on. But what is really nice that you can also, for this charge disk, prescribe your angular momentum distribution to come more closely to what you would like really expect to see in the observations. Okay, then I thank you for your attention, and I'm happy to answer questions.
Thank you, Eva, for this nice talk. I was asked to remind you to turn on your microphone again, your earphones again.
Does it work? Not well.
Yes, I hear the back call again. So are there questions? Okay, maybe I can Cheo?
I have a couple of questions, but I mean, if someone else wants to ask, then let me start with just the few. So first of all, thank you very much, Eva. Very, very, very nice talk. And so the first question is, can you briefly explain like what would be the difference in the step, the derivation step when you add rotation, like for example for Kerr black hole?
For the charge disk medium?
Without charge, just classical case.
Okay. Okay, I try to say this. Basically, there's not much difference. The only thing that you have to do is to use a more general metric. Let me see. This is very in the beginning. Yes, I mean, you have still this equation here. The UT will look more difficult. I didn't put it here, yeah, but it will contain the GT phi component. But their general equation is known, and for Kerr it's already well explored.
See, let me ask the second question. And so what is so you calculate the distance between the center and the curves, and you kind of use it to try to quantify this parameter in your parameter space. But my question is about what is the real physical observable from this thick disk? Because I think that distance shouldn't be a real observable. It's a coordinate dependent object. So yeah.
Well, not coordinate dependent because we used the proper lengths to calculate that. But still, you are right. You will not directly see this in the observations. I mean, in the observations, you will just see some radiative properties, some electromagnetic radiation that is emitted. So you would need to use your surface result and then calculate the radiative transfer from that.
I see. Okay.
Hey, are there any other questions? Maybe I can ask one which came to my mind. Do you know if anybody ever checked when you assume like nonlinear electrodynamics for the disk, like an uncharged black hole, but then small nonlinearities in electromagnetic theory, what would happen with the accretion disk?
Well, I once calculated this for this Aeon Beato Garcia nonlinear electrodynamics case. And there was not a large difference that you can really quantify. There you have the same problem that the space-time is constrained by weak field observations, and then you will not see a lot. But if you can find some nonlinear electrodynamic which gives you a different modification, then it's well possible that you can have strong effects.
Thank you. Are there other questions? If not, then maybe I can ask a second question. Usually when we have a supermassive black hole at the center of a galaxy, and we have also a dark matter halo, of course, we don't know what dark matter currently is, but do you think there will be any effects on the accretion disk which could be observed that may give us some hints on the dark matter, or the nature of the dark matter?
Well, if the halo is strong, certainly, because you will have an impact on the disks, serious maybe impact. But the question is if you can distinguish this from having a different mass of the black hole, or a different rotation of the black hole. Because it's usually from observation, you have rather large margins on these values. So I'm not sure. I'm just know that accretion of dark matter was also studied in a kinetic approach by some people in Krakow. And they use this Einstein-Vlasov system to do that. And I think they found rather large effects, but I would have to double check to be sure here.
Okay. Thanks. Are there any other questions? If not, I thank you again for the nice talk, and I would suggest we turn the recording off so that if people would like to ask questions, they can do that without the recording.